Hello and welcome to the last of the lectures in this week 10 of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will discuss the robustness of similarity-based reasoning schemes. Let's take a quick recap of the mechanism itself. So we are given a set of CISO rules, single input, single output rules of the form if x is ai, then y is bi, n of them. Given an input a dash, we use a matching function to compare the similarity between the given input a dash and each of the antecedents ai. For this, we use a matching function m from f of x cross f of x to 0, 1. So the similarity values are normalized between 0 and 1. Some of the examples that we have seen consistently are the Zardé's matching function and the one of Smith-Magre. Once an input is given, it is matched to each of the antecedents of the rules and the corresponding similarity values Si are held. In the second step, we modify the corresponding consequence of the rules using these similarity values. For that, we use a modification function. We know that even though j is essentially, the modification function j is essentially a function from 0, 1 cross f of y, the set of all fuzzy sets of y, to f of y, we know that it can be thought of as just a binary function on 0, 1, because essentially we are going to act on the membership values of the fuzzy sets defined on y. We have seen a couple of modification functions. We see that JML is nothing but essentially the Gauguin implication, and the second modification function is nothing but the product T-no. The third step, the modified consequence bi dashes that were obtained by using the similarity values Si to modify them using the modification function. All of these bi dashes, they are actually aggregated. So we are looking at a function which takes a few of fuzzy sets over y and converts them into a single fuzzy set on y. Once again, we have seen that we could use any binary function on 0, 1, but we would like it to be associative so that the aggregation is order independent. We can also have a post-processing step because the first three steps, they give you only a fuzzy set as an output. You could also defuzzify it to one of the elements on the output domain y. Similarly, instead of giving an input fuzzy set, one may actually have only a value from the domain x. Accordingly, we can fuzzify it to an input fuzzy set to be given to this SBR scheme. So in general, we said that this is the form of a fuzzy inference mechanism. X and y denote the input and output spaces. R of A, B, J denote the set of rules that we have. And the other symbol there, it captures all the inference operators. In the case of similarity-based reasoning, we know that it consists of a tuple of these many parameters or elements, where Px and Py are the fuzzy coverings on x and y, the input and output domains respectively. R of A, Bj gives you the fuzzy if-then rule base. The inference operations consist of 1, the matching function m, the modification function j, aggregation function g, and it could also often have the fuzzifier h and the defuzzifier g. Since we are considering SBR as a fuzzy mapping, clearly the fuzzifier h and the defuzzifier g, small g, are left out. The rest of the parameters remain. So in that sense, the corresponding system function, psi tilde, which can be looked at as a mapping from f of x to f of y, is given as follows. If you are giving an a dash to the psi tilde, we get a b dash, which is a fuzzy set on y. So b dash has to be specified on each of the elements y in the domain of the output domain y. It is given like this. So first we take a dash, compare it using a matching function and get the similarity value Si. Next, we use that similarity value to modify the consequent bi using the modification function j, and such modified consequence we aggregate using g. We have defined what is robustness. Towards defining robustness, we need the concept of extensionality. We made an assumption that we will remain within the realms of residuated lattices, which means T, the operations are coming from residuated lattices, and The most important ones are the left continuous T norm T and the corresponding residual implication, which we denote by IT, and in the case of infix notations, we are using the star and the implication, the arrow. So we are given a star equivalence relation E, and if we are given a fuzzy set mu, we say it is extensional with respect to E if this inequality is held. We have seen this being interpreted many times before. So essentially you can think of it like this. If x and y, E of xy is 1, that means we say x and y are equal with respect to this relation. Or in put another words, x and y are indistinguishable with respect to this concept that the relation E represents. Then we insist that the membership value of y to this concept should be at least as much as the membership value of x to this concept. Not all fuzzy sets are extensional with respect to a particular relation E. In that case, we extend it and we define the extensional hull of mu as follows. It's the smallest extensional fuzzy set with respect to E, which also contains mu. We denote it by mu cap, and we have a simpler formula how to obtain this mu cap given mu and E. Well, what is robustness? We have a space X on which we have a star equivalence or a T equivalence relation defined, and we say the system function obtained from an FIS psi tilde is robust with respect to this given T equivalence relation E if for every A in f of x we have that psi tilde of A is equal to psi tilde of A cap, where A cap is the extensional hull of A. We have seen that it means we cannot infer more precisely than the indistinguishability allows. Let's come to the robustness of SBR. For this, we need to define the extensionality of a matching function. Let E be a given T equivalence relation on X and M be a matching function. That means it's a function from f of x cross f of x to 0, 1. We say M is extensional with respect to this T equivalence relation E if for A dash, any two fuzzy sets A and A dash on X, we want that M of A dash is equal to M of A dash cap. Now what is A dash cap? It is the extensional hull of A dash with respect to the T equivalence relation. So essentially all we are asking is, if you match A dash to A, the matching function should give the same value as if you are matching the extensional hull of A dash to A. Are there examples of such matching functions? Well, the usual suspects, the matching functions that you have seen before, the Zardes and Smith-Margrave matching functions, in fact, satisfy this condition. We will see this immediately. Of course, we are once again going to assume that the operations are coming from residual lattice structure. In that sense, we can say that both these matching functions are in fact extensional with respect to the star equivalence relation. Let's look at this. We'll start with the Smith-Margrave function. This is given as min over x element of x I, so maybe it's A dash of x implies A of x. This is what we have. So first of all, notice that if you have a fuzzy set B which is smaller than C in terms of pointwise ordering, then this implies ms of AB is in fact greater than or equal to ms of AC. Now this is clear because if B is smaller than C, then B of x is less than or equal to C of x for ABC. Now when you put A of x here, then we know that this inequality in fact reverses. So if we take infix on either side, we get this inequality. So now we know that given an A dash, this is always smaller than its extensional hull, which means ms of A dash is greater than or equal to ms of A dash cap. So this is an inequality that is always available for us with respect to A dash and A dash cap. So what we need to prove is in fact the other inequality. We need to prove that this fellow is actually, the right hand side is bigger than the left hand side. So let's start with that. ms of a dash cap, this is equal to infimum over x a dash cap of x. Note that by definition we are switching places. Even though a dash appears here in second point, we are actually putting it in first position. A dash cap of x implies a of x. Now once again, the sup over t element of x, a dash of t star e of t comma x implies e of x. Now we know that in the residuated lattice setting, you can look at this as Ri Pi implies Q, which is actually equivalent to, we have seen this before, and Ri P implies Q. So taking this as Pi, you can write this as and over x and add infimum over t, a dash of t star e of tx implies e of x. Now we are in the residuated lattice structure, so that means we have also this property, taking this as p and q. P star q implies r is equal to p implies q implies r. So let's use that property here. This is p for s. A dash t implies e of tx implies a of x. Now we have seen this earlier too. Let's work it out. We know that et of x star a of t is less than or equal to a of x. Now we are coming from a residuated lattice structure, so now we know this also. If p star q is less than or equal to r, then this is equivalent to p implies r greater than or equal to q. So now this is p, this is q, this is r. So now we see that this if and only if e of tx implies a of x is greater than or equal to a of t. Now, so that means this quantity is greater than or equal to a of t. Now it appears in the second variable, second position for implication, where it is increasing. So the same inequality will hold. It's greater than or equal to xt. A dash of t implies a of t. Now this x is superfluous, and what we see, this is essentially ms of a comma a dash. Now what we wanted to show was that this quantity which we have taken here is greater than this quantity, and that's essentially what we have shown. So from here we see that ms is extensional with respect to the E star equivalence if the operations are coming from the residuated lattice structure. Let's also look at mz star. Sup over x, element of x, a of x star a dash of x. It is immediately clear that if a dash is less than, since a dash is less than its extensional hull, this implies mz of a dash is in fact smaller than mz star of a dash cap. This follows from the monotonicity of star. Because if you put instead of a dash, you could put a dash cap, then this will be smaller than that. So one way inequality is true. What we need to show is the other way. Now we need to show this is smaller than a dash. Let's start with that. A dash cap. Now this is equal to supremum over x, a of x star a dash cap of x. Now substituting for the extensional hull of a dash, supreme over t element of x a dash t star e of tx. Now we know that the star is actually a t norm coming from the residual lattice structure, which means we have it is left continuous, which means it's sup-preserving. So we can remove this outside. Supremum over x and t element of x a of x star a dash of t star e of tx. Now by commutativity and associativity, we can also write this as a of x star e of t comma x star a dash of t. Now we know that A is extensional. So now this is less than or equal to a of t, which means it is less than or equal to supremum over x comma t a of t star a dash of t, which is essentially equal to mz star a comma a dash. Now we wanted to show this right hand side is smaller than this left hand side. That's essentially what we have shown here because of the extensionality of A. So what we have shown is if A is extensional, then mz star is also extensional preserved on those points A where it is extensional with respect to E. So these are some examples of matching functions which are extensional. Now let's come to the robustness of an SBR model. Let us consider this model where we have Px and Py, which are essentially the fuzzy coverings on x comma y. We have the given fuzzy if-then rule base, and each of the AIs is in fact extensional with respect to a given T equivalence relation E. Let J be any modification function, G be any aggregation function, but what we want is M is extensional with respect to ET on X. So if AI is extensional, then we want that M of AI comma A dash should be equal to M of AI comma A dash cap. Under that condition, we can show the system function psi tilde obtained from the above model is in fact robust. Now how do we prove this? Let us look at this. So we know that psi tilde of A dash is equal to B dash. Now B dash of Y is equal to psi tilde of A dash at Y. Now this is nothing but G of I is equal to 1 to n, J of M of A comma A dash comma B I. Now clearly we know that M is extensional, so this can be written as M of AI comma A dash cap comma B I of Y. So this is the value that we need to put. Now what is this? This is nothing but psi tilde of A dash cap at Y. So clearly it follows, since M is extensional with respect to the given equivalence relation, T equivalence relation E, we see that the system in fact becomes robust. So for the robustness of an SBR, all we require is that the M is extensional with respect to the antecedents AI, which are themselves extensional with respect to the T equivalence relation E. So we need the antecedents to be extensional, like before in the case of FRIs, in the case of CRA and BKS, and we want that matching function also to be extensional with respect to the T equivalence relation E that we have. A quick recap of what we have done throughout this week. We noticed in the very first lecture during this week that different inputs can lead to identical outputs, but not always. So we asked the question, why does it happen? Then we came up with the answer that two fuzzy sets will give us identical outputs if they are related to each other in terms of extensionality. We defined robustness in terms of this. We discussed robustness of FRA schemes, that of composition rule of inference, and the Bangalore cohort subproduct, and also that of similarity based reasoning schemes. Once again, let's look at the CRIs and the FRIs in SBR in terms of the corresponding relation that we use. In the last 2-3 weeks, we have been discussing about interpolativity, continuity, and robustness. If it is CRI, we see that for interpolativity, R cap plays a role. If it is a solution to that fuzzy relational equation, then it has a solution and there can also be other solutions. However, when it comes to discussing robustness or whether CRI can be expressed as an SBR or the question of when theta is equal to 40, it is R check which actually comes into play. Dually, if you consider BKS, R check plays a role when it comes to interpolativity, but it is R cap which is important to discuss questions of equivalence between theta and phi, when a BKS can be looked at as an SBR, and finally to discuss the robustness of the underlying inference scheme. With this, we will wind up our discussions on robustness of fuzzy inference systems. In the next week of lectures, we will start to discuss on the monotonicity of a fuzzy inference scheme. Glad you could join us for this lecture. Hope to meet you soon again in the next one. Thank you.